understand that we had to each of them, as I explained, that if you assume that this, well, the disk addresses is, you know, refer to this as disk address. So what will be stored in each block, the beginning of each block, in fact, 2 or 3 bytes are used for that. A word 2 will be used for that, to store the disk address of the next block. So basically, it will store X, this will store Y, Z, and M. The problem is random access was extremely slow. In fact, as we saw, there's no random access as well at all. So what we did was to pull all these things up and put them in a table. As we put them in a table, then we started making a table, and for the table we put their disk addresses like S, X, Y, Z, L, and file A. This is a conceptual thing. How actually in memory they store it, it's a different thing, but that is in a table. And that table is kept in the memory. And we call it file allocation table. Take note of that. File allocation. As I said, FAT was an extremely popular file system. FAT 16, FAT 32, but 64 I can never think of because I used both of them. Extremely popular. And it was working well until the hard disk size started expanding. Okay. So when it started expanding, and remember that hard is much easier to expand the hard disk size. And that's exactly what started happening around that time when the FAT went obsolete. With 200 GB, as I mentioned, hard disk, your FAT table will get fatter and fatter, and almost 600 to 800 MB of RAM space because it is in memory, right? So 600 MB and 800 MB of RAM space is consumed just to keep that fat table right there on memory. That will not scale up. If you are using 1 GB RAM, then how much is left? Nothing left. Literally nothing left. Okay, 400 MB, and then your operating system will occupy, the drivers will occupy, and then the other things will occupy right there, and some space on the RAM. And literally, you will have nothing left for the user programs or user processes. But that didn't scale up. So we moved on to inodes. That is where we are. Inode is a structure. Okay. This is a structure very similar to the tree structure. It's a structure which is very similar to the tree structure. Now, all of you are familiar with this structure. We call the tree structure that keeps branching out, right? That's the beauty of it, because when you want to go to a particular item that has been stored on a certain branch, you just follow the path, right? So if you are trying to access randomly, you can access all of them. But one of the important key things about putting this inode structure, there are two things. The first one is it can grow infinitely. That means if you are storing a huge file, if your file initially it was of a limited size, a limited volume, but now it has started expanding and growing and growing. Well, you can let it grow, no problem. There won't be any problem related to storage as long as there is space inside your hard disk. Any little part left in any corner of your hard disk can now be utilized to store pieces of data. and they can be easily accessed because you are following this tree structure pattern. One other important thing is that the problem that was happening with fat table, the fat table, we try to keep it all the time on memory, and not only for one single file, but for all the files. The fat table contains all the details of all the disk addresses of all the files. Now you can imagine that, as I said, if your hard disk is bigger, and that means more space means more files means more blocks per file. So that's how the fat table ended up getting fatter and fatter. Okay. So if you don't go on that way, for inode, you don't have to keep the inodes or inode tables of all the inodes of all the files right there. The inode, if you can still remember when we're talking about directory, I told you that, of course, we learned that in the directory is a flat system file of type list, and for each item in your directory that you have organized there are some attributes, the file attributes, right? Like file name, file size, file type, and so on. The date of creation, date of modification, the author, the owner, all these things. But there's also one hidden parameter, and that is the file number. That is the inode number. That's not the file number, that's the inode. Now this inode number is so important because this inode number points at the beginning of the inode structure. And when you want, you double click on that link, on that item inside your folder, you basically, what you do, you tell file system to follow that inode number and access the entire inode structure, all the inodes, and load it on RAM. So on RAM, it's only the inodes of that particular file that you have opened. That makes a huge difference, right? So you don't have to keep everything, all the disk addresses of all the files in your computer at any given point. That was the real advantage. That was indeed the real advantage of inode, of the inode structure. Otherwise, it's tree structure. So you don't have to worry about this large number of files and large number of blocks. They're hogging your limited RAM space. Because we are not concerned, we are not literally concerned about our hard disk space. A hard disk is enough space, okay? But we are concerned about the RAM space. And somehow we just need to keep those inode structures, or those inodes, that inode structure, accessible on RAM, because if it's on RAM, the access will be much faster. In general, there are two ways to do that. The things that you can see, they have two parts. In fact, it's better to look at the picture. The inode, each file will be associated with a structure, inode structure. This is called the inode structure. The first part, there are two parts. One part stores the attributes. These are the file attributes. The other part, as you can see, a whole bunch of disk addresses. Now, some of these disk addresses, as you can see, the top ones, point directly to a data block. But as your file keeps expanding, okay, as we saw that was the case, the file keeps expanding. Now, the later part of the disk addresses, I reckon from 13 onward, and these are of fixed size. These are, by the way, of fixed size, not indefinite size. Each of them fixed size. So naturally, the next one, the last few, will not point to the data block, but will point to another block. Okay, see, that's called single indirect block, double indirect block, even triple indirect block, and that those blocks will again start doing the same thing. The first few point the data block, the last few will again go for 1, 2, 3, 1, 2, 3, 1, 2, 3, and you can see by following that 1, 2, 3 structure, in fact, layers and layers of indirection. Yes, you heard it right. Layers of indirection. Layers of indirection that you have to add. And these layers of indirection that you add will actually help it. Okay, help them to access the data. All right. So access data. What is data? These are data. In the triple case, these are data. This is only, remember, this is only one. You're talking about the first one. And these ones will do the same thing. Not all of them will be pointing to the data. The last few will again branch out to single, double, and triple. So each of them, they can keep growing, just like a tree structure. So you don't have to worry about storing the information. So if you want to access a file, all you need to do, or all the file system needs to do, is to capture this one. So that will be referred to by item. And in fact, all these node numbers, okay, remember, first of all, you have an inode number. Inode number is supposed to bring them right here. But when the file system tries to access the inode number, what it gets is basically an array. This is an array structure associated with each file, file X. And what is there? All the disk addresses of the nodes. All the disk addresses. This disk address, then this disk address, this one's disk address, this one's disk address. All the disk addresses will be stored right here. One per file. Each file has one such data structure or array associated with it. And where is it stored? If you can still remember just a few pages back, of course, in the previous class, we talked about in the partition, the layout, the first block was boot block, next block super block, third block free block, and finally a few blocks that stored the inode. And that array will immediately be loaded straight on RAM by using the inode number that is hidden as a hidden attribute in the directory link. When you click it, it will access this file node structure, this array structure that holds all the nodes, and this will then get loaded on RAM. From RAM, your file system can easily read all of them and quick access everything that is available. It knows all the nodes, and from the nodes, it can easily access the data. So there you get the strategy. So that is why it is quite an efficient solution. Yeah. It is quite an efficient solution that we are looking at. An inode structure was extremely popular. When Microsoft said that FAT went on up to 32, I can't remember FAT 64 because maybe it came to the market, but it didn't survive. So the best thing I can remember is FAT32. I used it quite a lot. But then came a new one that is called NTFS, so New Technology File System. This NTFS, a New Technology File System, brought in the concept of inodes. Well, it was launched by Microsoft, but I must tell you, like many things that Microsoft has brought to the market, not saying that everything, but many things, at least 50% of what Microsoft introduced to the market is kind of like a tailor-made version, okay, or paraphrased or reworked or re-engineered version of some old technology. And you will see this wonderful concept of this tree structure that we call the inodes. It came originally from Unix. It came originally from Unix. Of course, Microsoft did its own share of re-engineering or reworking on the same model. So they got the concept right there, and they introduced it as NTL, New Technology File System. Okay. Another mapping technique. The ones that we are looking at are all different mapping techniques. So that brings us to the next part, implementing directories. So we saw implementing files, important, implementing directories. So how do you implement directories? When it comes to implementing directories, as you can see, all you need to know, you can actually choose some attributes. That's in simple design. It's a list file. For each item in the list, you choose keep some important information about the file or just the file name and the inode number. Because the inode number will lead you to the root of the inode structure, and the base of the inode structure contains two parts. Remember, these are the disk addresses which will eventually branch out. But at the top is the file attributes. Just now we saw it. File attributes. So basically, you don't have to keep a lot of things inside file, inside a directory. You only have the inode number, and that inode number is this name and the inode number that will take you straight to the inode, and you can pick up or pull out those attributes and display it to your client. That saves the directory space, because remember, directory, we need to, when we talk about implementing directories, so how do you manage the space inside the directory? For example, one of the issues there that happens that we will discuss right here is about naming. So the attributes, okay, they can easily be replaced one by the other. That will not cause a problem. The one that will cause a problem, is the name, because the name can be of varied length. Okay. Now, if you allow the name, how will you allow this name to start out? Of course, you have to allow people to give their own chosen names. Now, that could be very short, AB, or that could be A, B, C, D up to Z. So the first approach that we had is, how about we give them a restricted, a limited number of characters, always file size. Well, for those who are giving a long name, it's okay. They know exactly how many characters they can use, maximum 255. But those who prefer shorter names, they will create a big hole. Isn't it? So that will be a problem. So to address that issue, we had another option. And another option that we had was the second approach. But in this case, I must remind you that one of the problems that happens in this case is the problem will come from the name. So in a directory, we have the name and then attributes, or inode number. So inode number is basically probably these address, right? So one disk address can easily be replaced by another disk address. Think about it. This is the source of the problem. Or in other words, one inode number can be easily replaced by another inode number. There won't be any conflict. If it's an integer value, then there's integer value. If it's a binary, 8-digit binary, then it's 8-digit binary. How about the attributes? Much of the attributes, if you choose to store attributes, then they are the same. If you talk about the extension of the type, if you replace docx with .exlx, in terms of the space needed to store docx, and in terms of the space needed to store .exlx or pptx, okay, these 1, 2, 3, 4, 5 characters, they are the equal size space. They need the equal size space. So if you remove a file docx, and you can easily fill it up with .exlx. So in terms of space, they need the equal amount of space. And the same with the size. Size is just an integer, or an integer associated with 2 characters. That's it. So they can be easily replaced, but the name will create a conflict. So the second approach was this. As you can see, we choose to have the length, the attributes, and the names were dumped right here and ended with a special character. Only after that, we start the second entry. Problem is still there. If you delete this file, you create a hole. Okay. How do you ensure that the next file that you want to choose, that you want to store right here, it will exactly fit into that hole? Well, as I said, the entry length will not create any problem. File attributes will not create any problem. The problem will come from the name, because the next one maybe has just AB. That's the name of the folder or the directory. So how will it fit in? It will create a hole. So that was a problem because of which we went to the final third approach. And as you will see, and probably many of you have started noticing it, that is all about adding layers of indirection. So that is what we are doing. We are basically adding layers of indirection. The layers of indirection that we are adding right here, and this is exactly what you are looking at. So what we do, for each file that we store inside the directory, we just store the attribute and the file length. Like the attribute, of course, contains inode number. Or if you just want to store inode number, just store the inode number. By using the inode, you can always access those attributes from your hard disk. Not a big deal. But then the name. What will you do with the name? So for the name, we use a pointer. And then the actual name is dumped at the end in a heap. Remember, there are quite a few structures. We didn't use the word stack. We said it's dumped in a heap. Now, when we say it's dumped in a heap, that means it's kind of piled up. Just imagine, in a corner of your room, you have a pile of newspapers, the old newspapers. That's called a heap of newspapers. And when you pull one newspaper out from the bottom of the pile, the rest of the pile, the rest of the newspapers on top, they will just rearrange themselves, and there won't be any hole right inside. So that is the concept. They're all dumped at the bottom. So that is the concept that we have right in here. So we need to put them in the right place. Otherwise, there'll be a chance of fragmentation. The last thing you want is inside the directory, because it is more common in the case of directories, because as we know that we keep changing our plans, right? We constantly cut and paste. Like you put in this folder, and later you change your plan. That no, I want to remove this folder, remove this file from this folder, and you cut it and paste it else. So because of these operations, it is quite tough to implement these file directory systems. So that is one of the things that we are looking at. Now, at least by using the third technique, a pointer, and as we use a pointer, naturally, we are using a layer of indirection. So that is everywhere. In fact, when we are talking about inodes, it's too was layers and layers of indirection. In fact, I wrote it down on the screen. Layers of indirection. And as I said, 100% of problems, any problem in computer science, whether based on hardware, architecture, networking, programming, you're all programmers, so you should remember that very well, that anything, any problem that you face in computer science can be solved, can be resolved by using layers of indirection. Layers of indirection that we use. Okay, so that is something that we always try to remember. Moving on from there, if you go to the next one, searching directories. How do you efficiently search the directories? Searching directories can be done by using the hash table or the cache. These are the two techniques that we have, the hash table and the cache. So what is the hash table? The hash table is, I think you're already familiar with hash table. And the hash table that we are talking about here is purely coming from the concept of everything that is located on memory. Basically, you may have known the hash sort and the different kind of sorts, the hash sort, bubble sort, tree sort. And these three things that we are talking about, if you study you may have studied about these things in Introduction to Computer Science. You can still remember. That we use the hash technique all the time. And the reason we use the hash technique to expedite the search operations, especially search and sort operations, is because everything that is done by using the hash technique is based on these memory locations. In fact, if you look at the hash sort, we always say the hash sort is the fastest one. But it is not the perfect sort. In perfect sort, we have an order that we call the alphanumeric sort. That means one will, if you are going for an ascending order, then it shall be A to Z, descending Z to A to Z, Z to A. But if you do the hash sort is very fast, but your final outcome may not actually match with your expected outcome. That means It should not be a proper alphanumeric sort. The reason is that in hash sort, the sorting will be done based on the memory location, or in other simple words, where exactly on RAM those particular values are stored. So based on that, it will do the sorting. Anyway, hash technology is one of the technologies that we use to expedite searching and sorting operations. Right. And now moving on, other one is cache. Cache is a well-known technique, and I think you already know that we can always cache it somewhere and we can track it down. In fact, you can see the cache. We maintain a cache which is called recently accessed files or something like that. I can't exactly remember. You have a folder, you have a spatial directory, that's a cache. Then all the recently accessed files will be updated right there. And naturally, like any other cache, it is of limited size. So some of the older entries or some of the files that you haven't accessed for a while, those links will be removed from the cache from time to time. So that is exactly what we do. Clear? The next one, shared files. Very, very important. Shared files. So what do we do in the shared files? In the shared files, remember what we are talking about is file server. And you want to share a file with your friend in real time. That's very important. What do you mean by real? Real time means just like what do you do? That you share a file and drive with your friend, and you and your friend, two of you, you can actually work together. Concept. This whole concept was introduced, and in fact, they became the pioneer in file sharing, in real-time file sharing, by Unix. In our times, we had to learn Unix to get a job in a company that might have a LAN-based co-working infrastructure. Okay, so that was of limited capability, but that is exactly what we had. The Unix gave us a platform. But of course, what Unix was giving us, the whole structure of the OS was totally different. The Unix structure was totally different from the, what do you call, our Windows structure, operating system structure. But anyway, the concept came from there. But now, at the moment, you know it very well when you use your Google Drive. But how do you do it? You create a file in your Google Drive. Okay, you upload a file or you create a new file, whatever, new doc file, Google Doc, and you want to share it with your friends, multiple friends. So all of them together at the same point of time can work on the same file. This is what we call real-time sharing. And what role does the OS play in that? And this is a very important part as well, because there are two techniques. The first one is called traditional linking. I've highlighted these words. Please, please, please remember these words. Okay. Hard linking or traditional linking. Basically, that means you share the inode. If you share the inode, then anyone can access your file. Inode is more like your private door key of your room. If you want 5 of your friends to use your room when you are not there, well, good luck. You can give them a copy of your private key. So they will come here and they will use your room. No problem. That is what we call the real-time file sharing. And that is what we call hard linking, okay, or traditional linking. But there's a problem. And the problem is, as you can see, the last sentence at the bottom. What does it say? And yes, you have to remember that sentence because I've seen questions where the person who set up the question basically quoted this sentence. A user can be billed for removed file. This scenario happens in hard linking or symbolic linking. So definitely in hard linking. Because just imagine that when you share your door key with your friends, then you have absolutely no control on him. So basically, whenever he wants, whether you are there at home or not, he will just walk into your room and do whatever he wants to do. If he does something bad, if he damages something, if he steals something, then you will never know out of your 5 friends with whom you shared your door keys, which of them actually did the job. How will you track them down? Try to get my point. It's impossible to point your finger to one person and say, you did it, because you shared your key with 10 other guys. So you just can't know, you can never know that who did the mischief while they were inside their room, inside their house. So hard linking had a problem, and that is exactly what I mean by a sentence, and this is often quoted on the exam paper. A user can be billed for the removed file. Okay, so that is what they usually do. So as you said, that this is something that we need to understand the problem of hard linking. So if it is a problem for hard linking, what is the solution? The solution is exactly what you do these days, called symbolic linkage. Hard linking. Symbolic, very, very important. What we do in symbolic linking, just try to imagine. So in case of symbolic linking, just imagine that there are 2 drives there. This is you, and this is your friend. So you are all in the drive space, and this is, as we say, this is the Google OS. Okay? So basically you are using the drive space. So what you do is your each space, each of them, you have a file right here that's open, and you want to share it with Mr. B. If you follow hard linking, we already talked about it. But if you follow the second solution, that's the symbolic linking, what you do is when you want to share the file, you so try to imagine that you right click on it, and you send a request. You want to share, you send a request to the Google OS. Google OS will create first, it will have and will create an extra inode and embed it into a file of type link, So that is what it will be doing. So it will embed it inside a file of type link. And once it is done, then all it has to do is to from the link, that link will be sent back to you, and you will pick that link and share it with the others. So that is essentially how this is supposed to work. What we mean, once you have the link to go for, and you take the link, and then you put it inside share it basically with your friend. So you create a link, and then this link will be handed back to you. It's not sharing the link. Google is not sharing the link automatically. Google, the moment you want to share the file, you ask Google OS, and OS will generate an extra inode for each link and will then create a link like this. And once it creates a file of type link, and then we'll share the link with A. Now that Mr. A has the link, Mr. A will share it with Mr. B. And you can use anything. I mean, you can physically share it. What I mean by physically means not necessarily you have to send by an email. You can send it by an email. You can send it in a chat message. You can send it uh, by using Facebook or whatever. You share the link with Mr. B and Mr. C and Mr. D and Mr. E and Mr. F and as many as you want. Okay? And now Mr. B will get the link. And Mr. B will click on the link. As he clicks on the link, he again reports back to the Google operating system. The OS, or rather the file system inside the Google operating system, will read from the link the embedded inode and will make a copy of this file, because with that inode it knows exactly for which file it created the inode, and will create a copy of that inode and will open it in Mr. B's directory. Is that clear? So by doing so, your file, there are quite a few benefits. First of all, the inode of the original inode of your file was never shared. It was never shared. So basically, since it was never shared, they can never access the original part, and they can never do anything inside this original file. They can do whatever they want to do on their copy. The copy is opened right there. And everything they're doing, if it comes to saving, I think we talked about it in when we were in memory management, that in real time, those things will be shared right there, because they are not only sharing the codes, but also sharing data. And we called it, you can still remember, copy on write solution. So these two things from the Google OS side, it is the memory management thing. And from the drive side, from your side, it's the hard disk file sharing. So these two things coordinate with each other. And as they coordinate with each other, you, in real time, whatever you do, you are doing on your copy. But this copy is quickly received by the Google OS, and Google OS will update it right here in the original copy. So basically, and this is the problem. This is the solution. Another important issue right here is this particular file that you are looking at. If Mr. B, because you shared the link with Mr. B on his Facebook. All right. Now, Mr. B clicks on it. The first thing he will have to do, he or she will have to do, they will have to log into Google account. It's Google Drive. So basically, if he is not a Google user, if Google doesn't know anything about him, and of course, Google knows more than what I know about me, Google knows more than what I know about myself. Okay, and we know it. So if Google doesn't know who that person is, or he is not a registered Google user, then he can never access a copy of that file by following that link. You get the point? So these two things work together. Literally, these two things work together, and what happens is once they work together, they will somehow they end up in doing the communication between themselves in the proper way. So the extra overhead of getting the file inode and extra inode needed for each symbolic link. And that is perhaps the only one that we have. So that is so that is what we have right in here. The copy on write strategy. The copy on write strategy, if you can still remember, is something that we studied earlier. So that is exactly what we do when it comes to sharing. So remember key points, important points for exam purpose. Hard linking, the problem. The user can be billed for removed file. So after hard linking, we go to symbolic linking. where basically we share a link. And we need an extra inode because Google is not going to share the original inode of your file. It creates a copy of that file, an extra inode for that link, and embeds it in the link and shares that link with you. Now, whoever you want to share that link with, go ahead and do it. No problem. But he or she, whenever he wants to use that particular link to access the same file in real time, will have to again go through Google. So this time, Google knows who is following which link and who is who. So basically anyone, because he has given multiple copies. So if someone does something wrong, he can easily later track it down, get who tampered the data. Okay, who tampered the data in which way. So that is the strategy that we use. That brings us to another part. And here we are going to talk about a handful of different types of file systems. Now remember, we already had FAT, memory allocation, and inodes. Those were different file systems like NTFS, FAT16, FAT32, and those file systems were primarily based on the way the disk was getting mapped. But here, it is more about that how they start doing the interaction. It is based on the interaction patterns. So what we have is a log structured file system. The first one. Log structured file system literally means that the entire disk is read as a big piece of log file. That means any transaction that takes place there will be noted down. But there's a kind of thing that we need to remember in log structure. We also had a journaling file system, and we will talk about it, and you have to understand what the difference is. In log structured file system, all writes are initially buffered in memory. Okay, and then from memory, they are dumped in one single part, one single sector, one single segment. Everything dumped together. Try to imagine everything written in the memory buffer, and from the memory buffer, everything literally dumped in one segment. Now, when you say dumped, that is literally what it is, because inside that segment, your data, your inode numbers, the file name, okay, all sorts of things will get jumbled up. So how will you find out that exactly where, in which part, okay, exactly where the inode is? Because we are not concerned about finding each piece of data blocks. Of course, that is our prime concern. But that can be done easily if only we can get hold of this inode. But finding the inodes is really tough. So what we did, we introduced an inode map indexed by I numbers. Okay? And entry I in this map will point to the inode on the disk, and the map is kept on the disk, is also cached, and most heavily used parts will be in memory most of the time, so you can quickly access it. This is an access pattern. You may actually say that isn't it also a kind of mapping? Yes, but as you can see that we are still using the old mapping technique, that is NTFS. In other words, the one that we were talking about, the inode structure. We are still implementing the inode structure. But on top of that, the way you copy those files, the way you actually write those files on your hard disk, based on that, we call it log structured file system. So in a log structured file system, everything goes inside one segment. First, it is buffered on the memory. Then everything, the inodes, directory blocks, data blocks, all will be mixed together. Okay? And inside a segment. The challenge here is to find out where is the inode. And to meet the challenge, we use an inode map. I have already highlighted them, these words, to catch your attention so you can actually try to remember these words and expressions. And this will be quite and important. All right. So we have this inode map. Remember previously we talked about disk map. Now we are talking about inode map. So don't confuse about these maps. You will get some other kind of maps. So maps are everywhere. It's all about mapping. I just took one picture. It could be that. JFS, journaling file system. What's the difference? Journaling file system is essentially the same log structured file system. No problem with that. Essentially log structured file system. You do the same thing, but you do it in a slightly different way. The journaling file system. The first step is completed and the system crashes. So in other words, one of the drawbacks of log structured file system, apart from this inode map thing, is everything is buffered in the cache, in the memory. The problem here, as we said, that if you the journaling file system, the JFS, one of the problems with LFS is try to understand that everything was buffered in memory. Remember, we said everything we take in the memory before we write it. Now, when this is the buffer, say for example, you are copying one file from here to there. Okay. So you basically put it into the buffer and then you transfer it. Or you are copying it from an external drive. Or you are writing it from RAM, whatever. So everything is buffered right on your RAM first. That was what was happening with LFS or log structured file system. The problem is that you didn't buffer it right here on the hard disk. Anything that is buffered on the hard disk is going to stay, going to survive the crash. But now if you buffer everything in the memory and then you dump everything inside a segment, that was a log structured file system. What will happen if there's a crash? If there's a crash, then your data, this data is gone. Okay, it will never can be retrieved because you didn't keep a copy right here. Or you have transferred half of it and the half of it crashed and disappeared. So to address this issue, what we do is basically not only from the buffer, but from there, the main actions that are supposed to be taking place, we write them down inside the hard disk. That's too temporarily. That is what we call a journal. A journal is a word associated with accounting. Okay. And accounting, if you have accounting friends, then friends studying accounting, then you can ask them. Journaling is a feature in accounting and how to maintain a journal for each transaction. Basically noting down all the transaction details. So just in case any transaction has a problem, you can track it down. What happened? When did it happen? When did you start it? And what went wrong? Yeah. It's the same thing that we do. We temporarily write the main actions that are supposed to take place right here inside our hard disk, and then the rest of it will go inside, just like log structured file system. If it crashes during the transfer, then you still have this information available for that particular transaction, and you can validate whether the transaction was successful or not, or if it is not successful, on recovery, you can rerun them to finish the entire transaction. That is what we call journaling file system. Both this LFS and JFS, they do ask questions from these two parts, so stay aware. Everything logged. You can see all the log files. Finally, it is the virtual file system, or VFS. Now, as the name suggests, why do we need it? Well, a couple of things I've highlighted here, because you are not from the Java, but it's Sun Microsystem. The Java guys. Okay, these are the Java guys because they brought in Java in 1995. And with Java came a new concept, and the word champion, their core technology that brought in the market is, again, add a layer of indirection. Or in other words, add, as we call it in Java, a layer of abstraction. If any of you have learned Java, you'll understand abstraction. Or sometimes in Java, we also call it interface. Okay, so basically what are you doing? That we basically, what we do, that there's a problem, and the problem that we are looking at is okay. The problem that we are looking at is this one. The different file systems, as I mentioned, can be implemented on different partitions on the same hard disk. So how will you know that at the end of the day, what kind of file system your process will be dealing with? So there will be a problem of interfacing. Because if it is in NTFS, it's a different interface. FAT32, FAT16 have different interfaces. So to get rid of this problem, what these Java guys did, as usual, they introduced a virtual file system, VFS, which is basically they took out the common components from, say, FAT and NTFS. The part which was common to FAT and NTFS, they pulled it out and put it into a layer that is called VFS, or virtual file system. These were the common parts, and these are the specialized parts. So now any process that wants to interact with any of these file systems don't have to worry about whether it has to deal with NTFS or FAT16 or FAT32. Because now you have what we call an uniform interface. It abstracted out the common part and put them in a uniform interface. So they will interact directly with a uniform interface, and this in turn will interact with a specialized part of each of these file systems. So that will be extremely helpful. VFS is very, very important. One of the most important is VFS. As you can see, these are user processes. Now they don't have to worry about whether they are interacting with file system 1, file system 2, or file system 3, because they have this virtual file system, which is again an uniform interface, and this was created by abstracting out the common parts, abstracting out the common parts. Okay, so that is what it all comes down to. That is what we call virtual file system. So we had, as we know, we have JFS, we have block structured file system, we had journaling file system, and now we have virtual file systems. These three, each of them in their own way, is very important. The next thing that we are going to talk about is file systems management and optimization. We'll just get started a little bit. Again, a bunch of theory that what to do and how to do it. Disk space management and optimization. How do we manage? As expected, our concern is free blocks. For that, as usual, we will have a bitmap. And the bitmap, we will mark the free bits. As you can see, how to keep track of the free blocks. The first method, using a linked list, is blocks. Each block holding as many free block numbers as will fit. The second method, using a bitmap. A disk with n blocks require a bitmap with n bits. Of course, we understand. The concern here that I pointed out when we were talking about bitmap in memory management, that bitmap right here, I actually pointed out over there, and now I mention it once more, that in memory management, especially in memory abstraction part, we had a bitmap, and the bitmap had zeros and ones. 0 for free, and 1 for occupied. Okay? Here, it's just the opposite. 1 is for free, 0 for So you need to be careful about that. Okay. Then 0 is for occupied or allocated, and 1 for free. That is the fundamental difference between these two bitmaps. But otherwise, these are all bitmaps. The second one on disk, the first one on RAM. Again, the same issue. What will be the block size? So we dealt with a common issue. It's all related to memory. Anyway, if it is large, it can be efficient, but waste of hard space. If it is small, it's good use of hard disk space to span multiple blocks. But disk accesses to read a file reduce the performance and waste time. Good compromise, performance and space utilization are inherently in conflict. That is a problem almost everywhere. They're always in conflict. So the size, the approximate size, it is good to remember. Just read 1 KB, just write 2.3 KB, read and write 4.2 KB. Okay, so these are something that you will have to remember. Quota, another word. If you're not familiar with this word, quota is something allocated to you, kind of like that during this COVID situation from the government, they gave a quota that every citizen with social insurance will get some benefits. But is a limited amount. That could be in terms of money, it was 2 million or 1 million. So you get that money, right? So you don't have to 2 million, I think. So 2 million. Every person will get a 2 million, benefit from the government. Okay. That is what we call the quota. So every person has a quota. It's 2 million. You can't ask for 2.5 or 3 million because that means you will be exceeding the quota. It's the same thing that it. Sometimes some of the students are complaining that you can't upload a file in LMS. It's too big. It's too big because you have a quota on your LMS. Okay, how much of file you can actually, the maximum size of the file that you can upload on LMS. So if you exceed the quotas are everywhere, then you can't use that particular feature. So when you go to shared file, it's more important when we talk about shared files. For example, Google Drive, when you open Google account, anything that comes to you free, well, it is free up to a point. Okay. If you want more space, you will have to pay. Right. So you know it by account, but I know that they exist. That you have a limit on your Google Gmail account and a Gmail attachment, and basically a server on the mail server, and then you have space limit on your drive. So to maintain these things, definitely the server will have to keep track of each user and some specific, we call them quota table, that specific information about what's going on in terms of their quota in their own space. If it's found that you are nearing the end of your quota, then you will be given some reminders. If you don't stick to it, naturally you will be warned. And if you still So that is what we call the quota table and the quota records based on your usage pattern. You will be given some warnings if you run out of quota. Next part is backups. How can we do the backups? There are two ways to do the backups. The first one is that we call physical dump and logical dump. Backup is important. Physical dump literally means every time you want to take a backup, you copy everything, including the free blocks. Everything, right? Start from zero and to the end. Okay. Everything will be copied every time. But that's a kind of a wastage of time, because what's the point of updating everything or backing up everything that hasn't been updated recent times? So we go for logical dump, physical dump and logical dump. Now, logical dump literally means you recursively back up only those folders from a certain point of time, and that is what they're talking about. Recursively dumps all files and directories found there that have been changed since some given base date. Of course, given base date means the date of last update. Last backup. So after that last backup, whatever backups you're taking, you can just go ahead and implement it. You get my point? So that is a more efficient way of taking backups. That really helps. This is consistency, not important very much. But if you see the patterns are the block in use and free blocks, they must pair with each other, because if it is in use, then later it will be free. So if you mark it one, then they actually maintain two tables where they much properly match. Okay. It was previously free. One is free in this case, and zero is occupied, so now it is occupied. So if there's a mismatch, it's not a big deal, but it will be corrected quickly by your file system. Okay, we will leave you here, and we'll come back and talk about file system performance. We'll start from there. It's a bunch of theory right now until we go to disk, where we'll find some algorithms. Yeah? After this one, we'll probably go to the disk. And many of you are there, 13. Swan Wong. Chi Kong.
Yes.
Ben Fook.
Yes.
So what happened? You don't want to submit? Hmm? What happened to you? All right, you don't want to submit right here. Up to you, but not the last minute.
I have problems with my computer, and now I use my phone, and the internet was very bad.
So the point is, when will you fix the problem? When a computer?
Maybe I'll find a place to fix my computers, because now I'm in a zone that
Somehow now I tell you that shops are opening, so you can just go out and with priority, you must fix it. I think you can go to the FP shop or any shops and you can fix it as quickly as possible.
yes,
Because if you don't do this assignment, this lab, if you don't submit it or you don't get at least a pass mark, you will not be allowed to sit in the final exam. And we just have 4 weeks left. This is week 6, already gone. Today is the last day of week 6. So you don't have much time left. Honestly, you can't just leave it to the when will happen, what will happen. You do it this weekend, you go out and get it done on an emergency basis. There's a hell of a noise right here. All right. Hey, for the rest of you, I think I will give you the attendance. I can't stand it. It's an extra neighbor who started doing these things from yesterday. I don't know how am I going to take the classes. For the rest of you, I will give all of you. I can't take attendance here. I need to talk to them. Is that okay? All right. There's a horrible noise going on. They all started doing it from yesterday. The next door neighbor on my wall. So see you next week. Don't forget to take the quiz if you haven't done it
Teacher,
yet. Yes.
you check me absent.
I really can't hear you, dear. I mean, can you send me the message? Send me a message. I really can't hear.
I sent a message already. Yeah.
Yeah, you send me a message. Oh, Swan Huang was there. Oh, feel free to send me a message. All right. There's a little bit of a problem here of this noise, and you will see it in a moment. I don't know how to resolve these problems. But anyway, I got a question here. Dong Fook, you asked me, should I remove VMware? It takes a lot of resource. It does. It does. And the point is, have you submitted your lab? You have already submitted your lab, right? Then remove. We don't need it anymore. Okay? Don't need to keep it. Yeah, I'll quickly go through it to see exactly. This is there, 1624, 1624. Okay, 1624, all of you have done it. So it's fine. Absolutely fine, no problem at all. Now, can anyone point it out where exactly should we get started? We were in somewhere in file directory, but can you point me the right place where we were? Were we somewhere here around this place? Can anyone tell me? Were we somewhere here? In the beginning. In the beginning. In the beginning means can you tell me exactly where? Did we talk about this one? Contiguous allocation, implementation of file. File implementation. Is it where we'll get started? File implementation. By the way, I alert you that there will be a horrible disturbance. I mean, I have to think about it. My next door neighbor started doing some horrible repairing things that will go on for a long time. The whole problem is I can't move to another place at this stage. There's no coffee shop or somewhere that I can sit down in peace. So there will be a little bit of noise. I'm trying to stay as far as possible, but you understand when you're doing it on your wall. You can't just stay away from that. But anyway, That's life. We complained, but in the apartment building, it's difficult to implement. Nothing happens. So we get started from here. I mean, as far as I can remember, because you guys are not giving me any lead. So we start from contiguous files, and if I can remember correctly, probably we came to this point, and then we moved in and didn't go too far. So we talk about contiguous memory allocations. It's all about how you implement your files. The way you implement your files is simply, the first option is contiguous allocation. Now, what contiguous allocation literally means is this is your file 1, this is your file 2, and this, for example, is file 3. So all next to each other. We'll quickly pass through. The problem is that if file 2 at the moment is of 10K size, then later if you delete this file, then you create a hole, a 10K hole. Deletion literally means a 10K hole. If you want to do editing, then you you open the file once more, and you start adding extra bits and pieces of data right in here. And that will probably make it 20K. Now 20K will raise a problem because 10K you can store right here, but there's an extra 10K that needs to be stored. So the problem was that it created internal and external fragmentations. Now, for these extra 10K, we have planned that we will, how about following the contiguous allocation, and we store it right there in these parts. So this is called, instead of F4, we call it F2, the second part of F2, where the 10K, extra 10K will be loaded. So essentially, we went to a linked list allocation strategy where the things started happening like in this way. So as you can see, they're disjoint. That means they're scattered in different parts of your RAM. But the challenge here will be to keep track of their disk addresses. So disk addresses must be noted down. And the way we follow this linked list, that's why we call it linked list allocation, is, say for example, these are the disk addresses that we have. These are the disk addresses. And the way we store it is right here, we spend a few bytes right at the top of each allocation block to store the disk address of the next allocation block. Right? This is why it will be stored right here. This is Z. It will be stored right here. ZL stored right here. It has nothing to store because this is the last block. Yeah. So that is a way we created a linked list. So we understand that everything is pretty sequential. If you want to go to this block number 3 and you want to pick up this address, where exactly in the disk block number 3 can be found, then the only way to go there is to start from here, because you can't randomly jump into this particular block to read the address. Again, so that is one of the issues that we will have to deal with. This is one of the issues that we will have to deal with, because we can't simply jump on this particular pattern. So we have this sequential So we have the sequential pattern of access. We have the sequential pattern of access, but that's all right. But when it comes to implementation, or of the random access, that we can't do anything about, because simply there is no way you can access it in the random way. As I said, that even if you want to jump straight, if file system wants to jump straight on this block, okay, then it will eventually have to start from there, because we were storing the disk addresses of each block in the previous block. So that is the problem. That is one of the problems that we will have to deal with. Right. So deal with what we did for random access, and also on top of that, that everything was, all these disk addresses were stored right there on RAM. Okay, right there on RAM. So naturally, all you have to do is to understand that we didn't put in the RAM, everything was put on the hard disk. And since everything was on the hard disk, it will take time to read all these addresses from the hard disk, because we say that anything that is read from the hard disk must take more time than anything that is read from the RAM. So reading from the RAM is always faster. So the solution that we proposed was to put all of them in a table. For each file, we will store their disk addresses. We store them in a file, in a table, and we'll put the table on RAM, on memory. And this table itself will be called the file allocation table. This will be called the file allocation table. Okay, so that is the one thing that we did. And we put the file allocation table, or FAT, as you can see right here. We put the FAT table straight on memory. By putting it on the memory, we could actually reduce the chance of getting things very slow, because we are putting it on the RAM, and that is exactly how we are going to deal with it. So that is exactly how you get to see how it works. But there was a problem with the FAT table. The problem with the FAT table.
Teacher?
Yes.
Yes, your mic has some sound that sound really annoying. I can't even
I
hear.
know, I can't even hear a complaint. I mean, I don't know what to do with that.
Okay,
I
I know.
mean, if you wait a minute, if you want to cancel this class, you can do it, and I will ask them to reschedule these classes on Saturday. Probably Saturday they don't work. It's going on.
It's okay, teacher.
We are all kind of like irritated about that. Just a minute, hold on. Hello? The students are complaining. So what you want to do? I mean, just let me know. I will cancel. I will ask APD to cancel this class.
It's okay. I will try to hear you.
Are you sure? It's a
Yes, yes.
hell of a noise going on right here. So should we cancel it on Saturday? Because even I mean all the members in my family, I mean we complained to the management, and the management said it will go on. They have given the permission to do it. You know it how it works. So the point is, if you want to continue, I can continue at the top of my voice. Of course, it's like not